So this is problem 269. Basically, we need to find the resultant force and the coordinate direction angles and sketch the vector of the resultant force. So we know that FR is going to equal F1 plus F2. And they're a little tricky here where they give us different angles for the two different ones. So F1 I think is going to be a little bit easier, but we know that F1 is going to equal F1 all times the cosine of alpha I plus the cosine of beta j plus the cosine of gamma k. And they give us angles so that we can figure out alpha, beta, and gamma. So alpha is that angle to the positive x-axis, so that's that 45 degrees. Beta equals the angle to the y-axis, which is going to be that 60 degrees. And then gamma, and this one may have tricked you, gamma is the angle to the positive z-axis. They give us the angle to the negative z, which is 60. So to get up to the positive z would be 120 degrees. If you're a little not uber confident about whether you got the alpha, beta, and gamma correct, you can always use that relationship just to do a quick verification or just check that you're right. So that, let's see, it's basically cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. So we can do that really quickly. So I did the cosine of 45 and squared it as 0.5. So for beta is 60. 60 cosine is 0.5 and square it. So that's 0.25. So now we're up to 0.75. And then gamma is 120. So cosine 2. So it was negative 0.5, which ends up being 0.25. And that equals 1. So when we verified that, that actually worked out good. So now we can figure out what the equation is because we know that magnitude of F1. So basically we're going to get, I'm going to make it in red, F1 equals that 400 newtons times cosine of 45 degrees I plus cosine of 60 degrees J plus cosine of 120 degrees K. And we can go ahead and multiply that out if we want to. So 400 times the cosine of 45, that's 0.707 I plus 60 cosine times 400, which would be 200 J. 120 cosine is negative 0.5 times 400 minus 200 K. And that's in newtons. So that's F1. And then we need to figure out F2 also. So F2 is going to be a little bit more complicated. I'm going to go ahead and box around F1 because we're going to need that when we figure out the resultant force. Alright, so I went ahead and just copied that figure over. So now we need to figure out F2. So F2, for this one, you'll notice they gave us the transverse and azimuth angles. So with this one, we do know it should be pretty easy to figure out the z component, so the k component. So I'm going to go ahead and do that first. So k, I'll move that all over to the right. It's going to be that 125 newtons, so 125 newtons times, and we just want that 3 over 5. So that'll just give us that z component because we know that common angle. For the x and y, it's a little bit more involved. So in the book, they talk about translating and figuring out that F2 prime. So that's just on that xy axis. So we take that z down to the xy axis. And to get that F2 prime is basically going to be that component of that, or the component on that x and y axis or plane of that vector. And so if we look at that common angle, it'll be 4/5 times that 125 newtons. So that'll get us down to the F2 prime, but then we need to find that x component and that y component of that. So for the x component, so we know the let's see, I'll do green, 125 newtons times 4 over 5. That just gets us down to that xy plane. And then we want that x component, so that cosine of 20 would give us that x component. So cosine of 20 degrees, and that gives us the I. I may not quite have room for that j there. I'm just going to move this down. And then for the j, for the y part of that, it's going to be negative, and it's that same 125 newtons times 4/5. So that gives us just that f2 prime. And then now we want that y component of it, so that'll be the sine of 20, because that's the opposite. So sine of 20 degrees j, and that's going to be plus that k component. So I'm going to go ahead and multiply that out. So f2 equals 125, 4 times 5 divided by, so that gives us 100 times that cosine of 20. So that's 93.97 I minus, and we just did that 125 times 4 over 5, which is 120 sine times, so that'd be 34.20 J plus, and that 125 times 3 over 5 plus 75 K. So now we have F1 and F2. So now we can figure out what the resultant force is. So I'm going to go ahead and bring this F1 over, just to make it a little bit easier for us. So we have F1 and F2. So the resultant force, so FR just equals that F1 plus F2. So that'd be that 93.97 plus 0.707 times I. And I did do, oh, I didn't multiply by times 400. I thought that was wrong. It was like, I was wondering why that number was so small right here. So 400 times cosine of 45. It looks like I just did cosine of 45. So that actually should be 282.8 I. And then it looks like I did right for the other ones. 282.8, so let me change that here. It's a good thing I caught that. I just noticed the number seemed a little weird. 282.8 I. So the resultant force, we're just going to add the I components. So 93.97. So we get 376.8 I. And then negative 34.2 plus 200. So we get plus 160. Oh, I can't write. 165.8 J. So I just added those two. And then for K, we're just going to add those two. So minus 125 K. And this is all in newtons. All right, so I figured out what that vector is. So to figure out the magnitude of FR, or we can just take the square root of each of the components. So square root of 376.8 squared plus 165.8 squared plus 125 squared, and just multiply that out. Take the square root, and we get 430 newtons. So that's that magnitude of FR. And then they also want us to give them the alpha, beta, and gamma. So we can sort of backtrack to figure that out. So let's see, the resultant force, all right, so now we have that that vector, and then we have the magnitude. So we can figure out the unit vector from this. The unit vector of that FR is going to equal that vector FR over the magnitude of FR. So that's that 376.8I plus 165.8J minus 125K. And that's in newtons. And then we're going to divide that by that 430 newtons. So that unit vector of FR is going to equal, just multiplying it out with the calculator, 0.876I plus 0.386J minus 0.291K. And now from the unit vector, we know that cosine of alpha is going to equal this component, cosine of beta is going to equal that, and cosine of gamma is going to equal that. So I'm going to bring this unit vector to the next page. So now we can figure out those angles. So cosine of that alpha, so that's that resultant force, is going to equal 0.876. So, and then cosine of beta is going to equal 0.386, and cosine of gamma is going to equal negative 0.291. And let's see. So gamma is going to equal 106.9 degrees. Beta is going to equal 67.3 degrees. And then alpha is going to equal 28.8 degrees. And so now we know those angles. So now we can draw it out like they had requested. Let's see, we know that the magnitude is 430 newtons. So FR equals 430 newtons. So let's go ahead and draw our axes. So we have X, Y, Z. We know that the angle to the x-axis is going to be 28.8 degrees. Actually, it may be a little bit easier. Actually, I may do it just based on this equation. So 377I. Let's see, what's the biggest one? Yeah, that's the biggest one. So each of those in about 100. Or whatever, so 377, and then for the y is 165.8, so something like this, 165.8, and then for the j is negative 125k, so that would be down in this direction, so it'd be a little bit less than that. And then down to that. So that's that resultant force. And then we can take a quick look at those angles to see if they seem right. So the angle to the alpha would be that 28.8. That seems reasonable from a not awesome sketch. The angle to the y-axis would be 67.3 degrees, and then the angle to the positive z-axis, so that would be up this way, would be that 106.9 degrees. So that seems reasonable. So that's the answer.